Welcome back to Discovering Geometry with Mrs. Berry. This is lesson 14. Today we're going to talk about special angles on parallel lines. We will be doing two more investigations today. And so remember that it is best practice to have a separate section of your binder or maybe a different spiral to keep all your investigations together. Get in the good habit of writing down the title, making your illustration in your notebook, or giving a procedure, and statement summarizing your results. Keep up with all the named conjectures too. Today we have a few definitions before we get started. We have a picture here, and this is two parallel lines right here, cut with this other line. So this is a transversal line. A transversal is a line that intersects two or more other lines in the plane. So this transversal intersects these two parallel lines. Corresponding angles. That would be angle 1 and 5 in our picture. So 1 and 5 are corresponding angles. Another set of corresponding angles would be 2 and 6. Can you find two other sets of corresponding angles? Hopefully you said 3 and 7 and 4 and 8. We also have what we call alternate interior angles. That would be angles 3 and 6 in our diagram. What other angle pair are alternate to the transversal? So 3 and 6 are on alternate sides of the transversal, and they're interior of the parallel lines. So these are our parallel lines. Inside would be 3, 4, 5, and 6, and then alternate to the transversal would be 3 and 6. There's one more pair of alternate interior angles. Hopefully you've said 4 and 5. That is another pair of alternate interior angles. Our last one is alternate exterior angles. So angles 2 and 7 in the diagram are alternate to the transversal. They're on opposite sides of the transversal, and they are exterior to those parallel lines. What is the other set of alternate exterior angles? You should have said 1 and 8. So let's get started with our investigations. Which angles will be congruent? For this investigation, you will need lined paper and a straight edge, a ruler, a protractor, and some tracing paper or patty paper. So we're going to start by drawing right on the lined edge, and then picking another lined piece and drawing another straight line. So these two lines are parallel, assuming that your ruled paper is parallel lines. So we label them L and K, and then we're going to draw a transversal. That's that line that cuts through both of those. It intersects, and we're going to label that M. Now we're going to label our angles 1, 2, 3, and 4 at the top intersection, and then 5, 6, 7, and 8 on that bottom intersection. We're going to get our tracing paper or our patty paper. We're going to put it over, and we're going to trace that top intersection. So line L and M and the angles labeled 1, 2, 3, and 4. Make sure you keep your tracing paper straight. If it moves a little bit after you draw a line, then just move it back so that it is exactly lined up. So what you're drawing on that tracing paper are angles that are exactly congruent because you trace them, so they're exactly congruent. When you overlay them on 5, 6, 7, and 8, do you see that 1, 2, 3, and 4 are congruent to 5, 6, 7, and 8 respectively? So that's angle 1 on our tracing paper, but down underneath, that's angle 5. So 1 is congruent to 5, 2 is congruent to 6, 3 is congruent to 7, and 4 is congruent to 8. We can then even measure these angles. Just looking and remembering, 1 and 4 are vertical angles. Remember from our previous lesson that vertical angles will be congruent. So if we measure angle 1, then we should find that angle 4 is congruent, is the same measurement. So in my picture here, angle 1 and 4 both measured 125 degrees. From our linear pair, if 1 is 125, 2 should be what to equal 180? So 2 should be 55. 3 is a vertical angle, so it should also be 55. If we make these same measurements for 5, 6, 7, and 8, we will find that 5 is 125, 6 is 55, 8 is 125, and 7 is 55. Now, again, these are measurements off of what I drew. Yours should be a little different. However, they should match up. So in the end, there's only 2 measurements for all 8 of these angles. They are either 125 degrees or 55 degrees. Perhaps on yours, they're a little bit different, but the 2 different measurements that you get from your 8 angles should add up to 180 degrees because you're going to find linear pairs in every adjacent set of angles. That also means that when we compare, 3 and 6 would be alternate interior angles, and they both measure 55 in my diagram. 4 and 5 are alternate interior angles. In my diagram, they both measure 125. They're congruent. The alternate exterior angles are 1 and 8. In my diagram, they measured 125 each. So that means they're congruent. And 2 and 7 are also alternate exterior angles. In my diagram, they both measured 55. They're congruent. So we have a lot of conjectures from this investigation. First, our corresponding angles. So when we first overlaid 1, 2, 3, and 4 on top of 5, 6, 7, and 8, we found that all of those angles matched up. If 2 parallel lines are cut by a transversal, that's the picture we drew, then those corresponding angles are congruent. So corresponding angles are congruent when we have 2 parallel lines cut by a transversal. When we went and measured all of our angles and then actually used our deductive reasoning to correlate them between vertical angles and linear pairs, we found that our alternate interior angles were also congruent. So if 2 parallel lines are cut by a transversal, then the alternate interior angles are congruent. That would be our alternate interior angles conjecture. Alternate exterior angles conjecture. We also found that our alternate exterior angles were congruent. So if 2 parallel lines are cut by a transversal, then the alternate exterior angles are congruent. We can combine all of these 3 things into one conjecture that we might call the parallel lines conjecture. If 2 parallel lines are cut by a transversal, corresponding angles are congruent, alternate interior angles are congruent, and alternate exterior angles are congruent. What about non-parallel lines? Do you think this would work with non-parallel lines? Let's give a quick sketch. And get my pen out so that I can see. Here we draw a line, and then we'll make sure that it's not parallel. We're going to make it come out a little bit. Now I'm going to draw my transversal straight up and down that cuts through. So 1, 2, 3, 4, 5, 6, 7, and 8. Well, see, I drew 5, 6, 7, and 8. They look very close to 90 degrees. What about up here? None of these look close to 90. This is definitely an obtuse angle, and 2 is definitely acute. So if we were to compare corresponding angles, 1 and 5, they're definitely not congruent. What about our alternate exterior angles, 1 and 8? Also not congruent. Again, 8 looks a lot like a right angle, and 1 is definitely obtuse. What if we compare alternate interior angles, maybe 4 and 5? Do 4 and 5 look congruent? No, they don't. So this does not work with non-parallel lines. Remember that we can always go backwards. So what happens if we want to investigate the converse of parallel lines? So let's do our second investigation. We're going to need paper, a straight edge, and our tracing paper. We're going to start by just drawing 2 lines that intersect. One of them will be our transversal. We're going to put our tracing paper on top, and we're going to trace these 2 lines. When we do that, we know that the tracing paper and the paper underneath have congruent angles because we have just traced them. They are exactly the same at this moment. Then we're going to take our tracing paper and move it down. And if we keep that transversal lined up as though it's the same line, then we're going to trace the underneath line again. So now we have 2 lines cut by transversal, and we know that all those angles are congruent because we traced the original one twice. So we know that those angles are the same. Now we're going to measure these lines throughout and see if these lines are parallel. If we use a ruler to measure the distance between the 2 lines and we see that it's the same distance between them everywhere, then that means those lines are parallel. So in this case, we have proven that if we keep corresponding angles congruent, those lines will be parallel. So that's part 1 of the converse of parallel lines conjecture. Now part 2, what about keeping alternate interior and alternate exterior angles congruent? We're going to start with that same intersection of lines on our paper, and we're going to trace on our tracing paper again. And so we are making congruent angles right now. Now, instead of moving that tracing paper down, what we're going to do is turn it 180 degrees. So now we know that the alternate interior and alternate exterior angles are congruent because we took that same intersection and we just turned it around. We're going to trace on our patty paper the original lines, and now we're going to be measuring, are these lines parallel? The distance between the lines are the same throughout. When we turned our paper around, we were making the alternate interior and alternate exterior angles congruent. When we measure the same distance between those 2 lines, we know that those lines are parallel. So the converse of the parallel lines conjecture: if 2 lines are cut by a transversal to form pairs of congruent corresponding angles, congruent alternate interior angles, or congruent alternate exterior angles, then the lines are parallel. They are. So this conjecture works in its converse. The last thing we have today is to do a little bit of algebra review. So we're going to review what a slope is. Slope is the measure of steepness of a line or even a hill or a mountain. Slope can tell us the rate of change, how fast or slow something is increasing or decreasing. If a graph was distance versus time, slope would tell us the speed, how fast or slow you are increasing or decreasing your distance. So that would be your speed. Here's a fun picture. The guy going up the hill has a positive slope. Straight across would be a 0 slope. Going downhill would be a negative slope. And if it drops straight off, that would be undefined. A review of how we calculate slope. Here's a line in blue and 2 points on the line. To calculate slope, we find the ratio of the vertical distance, that's the up and down, traveled to the horizontal distance traveled. So the up and down we call the rise, and the horizontal we call the run. So we often say that it's a ratio of rise over run because it's it's vertical over horizontal. So if slope is rise over run, rise being our vertical change and run being our horizontal change, vertical being our change in the y values of the points, horizontal being the change in the x value of the points, then we can come up with this formula using 2 points on the line. It doesn't matter how close together or how far apart these points are, as long as they are exact points on the line. Most of the time, it's easier to get whole numbers, so I always choose where my graph intersects those grid lines so that I can use whole numbers in my calculations. But honestly, it doesn't matter. You could do decimals or fractions as long as you are exact and those points are on the line. So if we take the points x1, y1 being the x value and the y value of 1 point, and x2, y2 being the x value and the y value of another point, a second point, then we can use this formula up here to find the numerical value of the slope. I'm going to use on my graph 3, 2 as my point 1. So this is going to be my point 1, and this is going to be my point 2. So 3, 2 is going to end up being my x1, y1. And 7, 5 is going to be my x2, y2. Now I'm going to use that slope formula of y2 minus y1 over x2 minus x1. I'm going to plug in my y2, which is 5. I'm going to plug in my y1, which is 2. So 5 minus 2. Down at the bottom, I'm going to plug in my x2. So my second x value is 7, and my first x value was 3. Now I will subtract on the top. 5 minus 2 is 3, and 7 minus 3 is 4. So the numerical value for my slope is a positive 3/4. You could also draw it on your graph. This rise is how far did I go from my y value from my first point to my y value of my second point. And I went up by 3. My run is how far across I went. I went forward by 4. So rise is 3 and run is 4. So my rise over my run is 3/4. You should be getting the exact same numbers whether you use the formula with the points or whether you maybe draw a slope triangle and count the distance on rise and run. So this is the last lesson in chapter 2. There's also a fun exploration on fractals starting on page 135 that you could look at the end of chapter 2. And I want to make sure that you review and check your understanding for both chapters 1 and 2 before moving forward.